problem. Show that root 2, root 3, root 5 cannot be the terms of an AP. Root 2, root 3, root 5. Can we consider them as the terms of an AP? We have to prove that. So let us assume that they are in AP, or they are the terms of an AP. So we can call the first term as a pth term, second one qth term, the other one rth term, pqr, consecutive terms, and let us assume that they are in AP. So root 2 is a pth term, root 3 qth term, root 5 rth term. So let's write. Then root 2 is pth term, that is a plus p minus 1 into d. Root 3 is qth term, that is a plus q minus 1 into d. Root 5 rth term, a plus r minus 1 into d. So if you assume these terms are in AP, the common differences are the same, or we can take the ratio of the common differences. So let's find root 3 minus root 2. That is a plus q minus 1 into d minus a plus p minus 1 into d. That is a plus qd minus d minus a minus pd plus d. These terms get cancelled. We will get q minus p into d. Root 3 minus root 1 d. Like that. Root 5 minus root 3. A plus r minus 1 into d minus a plus q minus 1 into d. That is a plus rd minus d minus a minus qd plus d. Here again these terms gets cancelled. We'll get r minus q into d. So we have found out the common differences. Let's take the ratio. Say root 3 minus root 2 divided by root 5 minus root 3. We get q minus p divided by r minus q. So we have to prove these terms cannot be in an AP. So we are presuming it as an AP. So root 3, root 5 are in AP. We are assuming. Then we are finding out the common differences and the ratio of it. So we have found out that the ratio is a rational number. This is a rational number. Why do you say it's a rational number? PQR, pth position, qth position, rth position, PQR are natural numbers. So this is a ratio of the natural numbers or integers. So ratio of numbers that can be expressed in a fractional form are called rational numbers. That can be expressed as a ratio. Such numbers are called rational numbers. So if this is a rational number, this one should also be a rational number. But it contains roots. So let us try to convert that into a rational form by taking the conjugate of the denominator and multiplying both the numerator and the denominator by the conjugate, and that is called rationalizing. That process is called rationalizing. So let's try to rationalize the left hand side LHS. So root 3 minus root 2 divided by root 5 minus root 3. Multiply the conjugate of the denominator, that is root 5 plus root 3 is the conjugate. So multiply both the numerator and denominator. Root 3 into root 5, root 15 minus root 3 into root 3, root 9, 3. Then root 2 into root 5, root 10. Then minus root 2 into plus root 3 minus root 6 divided by, this is of the form a minus b into a minus a plus b. So a square minus b square 5 minus 3 2. So is this a rational number? Again, it contains terms that are not perfect squares. Square root of 15. So 15 is not a perfect square. It was 25, or this was say 100, or this was say 64, then we can say this is a perfect square and the root will be an integer and both the side will be rational. But this is an irrational number involving roots of numbers that are not perfect squares. So this is an irrational number. So the right hand side is not equal to the left hand side. So our assumption is wrong. Our assumption was the terms are in AP. Now we have proved the contradiction is the right answer. That is, they are not in AP. The right hand side is rational, the left hand side is irrational. So this is the method of contradiction. We have proved that we have contradicted the earlier assumption that these terms are in AP. We have contradicted that assumption by proving that the right hand side and the left hand side are not the same. One is rational, the other is irrational. Okay? See.